And we come to our final video in the Modelling with Algorithms series. We're going to look at the 3 network problems that we looked at in our previous video. That's the 3 bipartite problems. And we're going to look at some software outputs and interpretation of those in this video. So the first problem we looked at was the matchings problem. And this considers a bipartite graph with some connections between the 2 groups. And the idea of this is to choose as many arcs as possible from the arcs that are given, such that not more than one arc is connected to every element in this group, and not more than one arc is connected to every element in this group. So just by looking at the number of elements in each group, we know that the absolute maximum number of arcs that we can choose is 4. But don't assume that's the case just by looking at it, although this is a fairly small case, so you can probably spot a solution. But these questions are not about finding the solution, it's about writing the linear program and interpreting the output from the software. So last video we looked at writing the linear program for this problem, and we ended up with this. So we wanted to maximize m, which is the sum of all these variables, and these variables are called indicator variables, such that if it's the number 1 in the optimal solution, then that means we are using that arc, and if it's a 0, then we are not using that arc. It's quite simple as that. All the variables are either 1 or 0. And then we've got these constraints. Okay, so this top constraint, AW plus AY is less than or equal to 1. That ensures that not both of these arcs are chosen because we don't want more than one arc connected to node A. And then the same is true for the other 8 nodes. Okay, so that's the program that we got. I then ran this through some software, spreadsheet software specifically. So this is what it looked like before I started running it. This was the spreadsheet window which allowed me to solve the problem, and the output, which is the important bit, looked a little bit like this. And you could be giving something like this in the examination, and you would need to interpret what this output means relative to the original problem. So what we can see here is running the linear program. The objective has come out as the number 4, which, as we said earlier, is the maximum it could possibly be. So it's found a matching of 4. And then it's got a list of all the 10 variables, and 4 of them are the number 1 and 6 of them are the number 0. There are lots of decimal points after them. That is not uncommon in an output, especially one for modelling with algorithms examination. So that's why I've put it in here so you're familiar with it. It's just a bit of a diversion tactic, really. The important part is it's chosen AY as being 1, BX as being 1, CW as being 1, and DZ as being 1. Over here I had my constraints. A has got an arc connected to it, B has got 1 arc, C has got 1 arc, D has got 1 arc, and E doesn't have any arcs connected to it. And then W, X, Y, and Z all have 1 arc connected to it. So those that was just the constraints as part of the workings out. So what a question may ask you to do is it may ask you to therefore draw the solution to the matchings problem. So we would have to draw out a network. Okay, got A, B, C, D, and E. C, D, and E, and then on the other side of the bipartite graph we've got W, X, Y, and Z. And the fact that AY is the number 1, that means we are selecting worker A to go with job Y, and then BX, worker B, is going to job X, CW, so C is going to W, and then DZ, and E doesn't have anything to do. Okay, but we knew that had to be at least one worker didn't have a job to do because there were 5 workers and 4 jobs. Okay, so that would be the solution that the output of the software gives. That's not going to be necessarily a unique optimal solution, but it's the one that is given by the software output. So that's the one that we need to work with for the question. Okay, so that was the first one. The second one was an allocation problem. So in this problem we had, again it's bipartite, we've got 5 nodes in one half of the network and 5 nodes in the other. For this problem we have to have the same number of nodes in each group. So in this case we had 5 in each group, and it has to be a complete bipartite graph, which means every element in one group, or every node in one group, must be attached directly to every node in the other group. So we end up with this n squared table of connections. Okay, in this case n was 5, so 5 squared. And the linear program we got for this problem was this one. And what this would do is it would, again, using indicator variables, it would choose 5 of these 25 numbers such that 1 from each row and 1 from each column were chosen, which would then minimize the total cost. Okay, the total number, the total of all those 5. So this was the program that we wrote. If you're unsure where this comes from, just check out our previous video and I explain it all in there. So again, what I've done is I've taken this problem and I've run it through a spreadsheet solver again this time. And this was my output this time. So it's programmed slightly differently. It's a really big table like this. I don't think you'd necessarily get anything like this in the exam actually. But I see no reason why you wouldn't be able to interpret this table. So we've got column headers across the top. It's all of our variables. There are 25 variables in this problem because it was a 5x5 grid. And then the variable value, these were the values that could change. The linear program could change those values. The objective function, so these are the coefficients of those variables. And that is my objective there. And then I have my 10 constraints there. Top constraint, for example, made sure only one arc was connected to node A. And then this one to node B, one to node C, D, and E. And then I also had V, W, X, Y, and Z as well. Okay, so interpreting this, well, the variable value is the important row in this one, and then this number here is important as well, because that's the objective. So AX is 1, BY is 1, CW is 1, DV is 1, and EZ is 1. So those are the 5 that are the number 1. As I said earlier, we would be choosing exactly 5 of these numbers. 1 from each row, 1 from each column. So we're choosing AX, so that's that number there. Okay. I guess it's not much of a surprise, it's the smallest number in that row. BY, okay, 11 there. CW, there. DV, oh, that number there, not that number there. DV, and EZ. That's the other one, so that's that number there. Okay. Right. So these are the 5 numbers then that were outputted by the linear program, and that minimized the total cost. Again, it doesn't necessarily mean it's the unique solution to the problem, but it is optimal. There's no better solution. In other words, you can't take 5 numbers, 1 from each row, 1 from each column, that sum to less than these 5. So they should sum to 49 according to the output table. So 23, 31, 42, 49, so that's good. And we can see that indeed 1 from each row and 1 from each column have been chosen. Okay. Are there any surprises there? Probably not. I mean, it's not always the smallest number in each row or column, but that's not unsurprising. This one here, the 14, that was the second highest actually in this column, but it just worked out like that. I guess D is expensive everywhere. So it's not always intuitive as to what your answer is going to be. So that's why we use software to solve these problems. If you didn't use software, then there are, I think it's 5 factorial different ways of choosing 1 from each row and column. So 120 combinations to go through by exhaustion. Much better to consider the linear program. Okay, and then if you were to asked to draw the network as well, then we would draw the network. And so again, you'd have your bipartite network. So your nodes are in 2 groups, A, B, C, D, and E, and then V, W, X, Y, and Z. A is connected to X, B is connected to Y, C is connected to W, D is connected to V, and E is connected to Z. And then I would put the weights of those on this network as well. 8, 11. Make sure it's clear which number's going with which arc as well. That's why I put all the arcs in before I put the numbers in. Okay, something like that. So the question asks you to make sure you actually draw then the final answer. Okay, and then one final problem that we looked at was the transportation problem. This was the more complicated of the 3 that we looked at. This time I'm going to use an online linear programming solver to solve it. Just to remind you of this problem, we've got 3 warehouses with supplies attached to each of them. Then we've got 5, I call it shops, I think, and with a demand of each of those. The total supply, which is in this case 100, will equal the total demand, and our job is to take all of this 100 supply and distribute it amongst these 5 shops so that all of the demand is met. And this table here represents the cost to transport 1 supply unit from each warehouse to each shop. So for example, here it would cost you 9 units of money to transport 1 of those 50 from warehouse A to shop V, and so on. So the linear program that we got from this was this one. We want to minimize the total cost. This linear program does not use indicator variables because now AV, for example, will represent how much stock we are taking from warehouse A to warehouse V. But they are still integer values. We don't want to take half a piece of stock. So although they're not restricted to 0 and 1, we are still restricting them to being integers, positive integers, or non-negative integers. And then these were the constraints. That ensured that all 50 stock left warehouse A, all 35 stock left warehouse B, all the stock left warehouse C, and then these 5 ensured that the demand was met for each shop. So the 3 coming into shop V needed it summed to 10, and so on. So that was the linear program for that. You need to know how to do this, by the way. And then the input to this linear program, you wouldn't be given this in the exam, but it was just some linear programming online solver I found online. So I popped in all the constraints according to how they wanted their code written, and then the output looked like this. Now it's quite small. Probably should have made it bigger, but this is my output. It's a big table, and our job is now to interpret this table. So we are looking for, in fact, if I put that down, I think I can zoom in a little bit. There you go. We are looking for this column here, because this gives us the value of the variables here at the end of the program. So this is the optimal solution. This is after the software has run. So we can see that AY is non-zero at 15, AZ is non-zero at 35, BW is 10, BX is 20, BY is 5, CV is 10, and CW is 5. So those are my outputs. And we can see that a warehouse delivers stock to multiple shops. So let's pop that solution on here. Let's see kind of what's going on. Let's zoom back out. Okay. So there was 15 going from A to Y. So 15 of those there. 35 going from A to Z. So that actually sums to the 50, which is good. BW was 10. BX is 20. And then BY was 5, and then we had CV is 10, and CW is 5. Okay, so that's my output values. Anything that's not there is a 0, so nothing went from those warehouses to those shops. Let's get rid of those. Okay, excuse me. So what we can see here is from warehouse C, 10 of its stock is going to shop V, and 5 of its stock is going to shop W. From warehouse B, 10 of it is going to W, 20 of it is going to X, and then 5 of it is going to Y. And then from warehouse A, 15 is going to Y, and 35 is going to Z. Okay. You can check all the demands. Okay, the sum of those 3 is 10, the sum of those 2 is 5. Some of those 3 is 20, some of those 2, or 3 is 20, and that is 35. So all the supply columns, rows, and the demand columns all match up to what they're supposed to. So that was an optimal solution. Again, it's not guaranteed to be a unique optimal solution, but we can guarantee that it's not a better one. So if you were to sum up all of that cost, i.e. 10 times 9 plus 5 times 14 all the way up, then you will not find a better outcome. And the total cost of that was not actually given on the table. So it was on a different screen, which I didn't copy onto the output. So the question may ask for the optimal output, so we would have to run those values through on a calculator. So we're going to have 9 times 10 plus 14 times 5 plus 12 times 10 plus 11 times 20 plus 10 times 5 plus 10 times 15 and then plus 9 times 35. Okay, so the optimal is 1015 so that was the optimal solution there. Yeah, so this video is all about taking the output given to you in the question and interpreting that back in the context of the question. Okay, one final thing that I want to talk about very briefly is the actual linear program itself. So for all 6 cases, so the 3 bipartite network problems that we've just looked at and the other 3 that we looked at in a video a couple of videos ago, it is unlikely that you will be asked to write the whole program, purely because they are quite long to write, and that's not a good use of exam time in terms of an assessment. So what they'll tend to do is they may give you most of a program and you need to fill in some blanks, or they might redact a little bit of it and you need to say what that coefficient is, or they might ask you to explain what this constraint does. Why is it there? Why is it necessary? What does it do? Those types of questions. So it is useful to know how to write the program from the problem, because then when a question asks you about a constraint or about a coefficient, you'll be able to answer that with confidence. If you have any questions on this, again, as usual, please just drop a message in the comments and I'll get back to you when I can. Thank you very much for watching.